So today we are going to study Ampere circuital law. What Ampere circuital law? It is as in static electricity we have studied Gaussian law, Gauss law, the charge enclosed in a electric flux linked with charge enclosed is equal to Q upon epsilon 0. So in same way in magnetic similarly we have Ampere circuital law as alternative form of Biot-Savart law. Okay, as we have a Gauss law in the form of Coulomb law in electrostatics, similarly we have Ampere circuital law as an alternative form of Biot-Savart law in magnetism, magnetostatic you could say. An Ampere circuital law gives a relationship between the line integral of magnetic field is in total current I which produces this field. So let's read it. It states that the line integral of magnetic field B around any closed circuit is equal to μ0 times the total current I passing through this closed circuit. This means line integral B dot dl is equal to μ0 into I. The line integral of magnetic field around any closed circuit is equal to μ0 times the current passing through that closed circuit. Or in very simplified form, it states that if field B is directed along the tangent to every point on perimeter L of closed circuit and its magnitude is constant is along the curve, then BL complete length perimeter BL is equal to μ0 I. It's a different way of saying the same thing. So we have to prove it. We have to prove that integral B dot dr is equal to μ0 I. Okay, so let's add the slide. Now page number 2. To prove it, so let's say it, we are making it proof. Okay, proof of the quantifier. So consider an infinite long straight conductor carrying current I. Conductor carrying current I. Let's use it. Current है, so let's use it. Okay. My mistake. Okay, let's make it. I just rub the direction and make it current line. Rub the whole thing. Direction, so that current I is flowing in upward direction. So if you want, I can increase the size. Okay. From Biot-Savart law, the magnetic field B, due to the current carrying conductor at any point at a point distance r, is given by a circular, following Biot-Savart law. The B value B is equal to mu 0 I upon 2 pi r. This is the value of magnetic field around at point r, at a distance r from circular loop. And if you remember, the magnetic field is in plane perpendicular to the screen. That means if I draw, let's draw a okay. Okay. And as per the rule, the direction of magnetic field, if you remember, if you from right hand thumb rule, if the thumb represents the direction of current, then the curl finger represents the direction of magnetic field. Okay, so as you can see, it is similar. So the B field is directed along the circumference of that circle of radius r with wire at center. The magnitude of magnetic field B is same for all points on the circle. The magnetic field B is same for all points on the circle, because it is at equal distance from the circle. Now we consider a very small current element dl along the circuit. This time we are not considering a part of conductor. This time we are choosing current. Okay, I'll choose a circular. I don't know how to do undo. Okay, let's make it broader. Can you see this red one? Okay. So this is a part of circle we are choosing. Now this is length of this is dl, and to represent the length we simply draw a tangent. Okay. So from this I'll try to draw a tangent. Okay, so this is a tangent. And from center of the circle, and if from the center of the circle, if you remember any line, if I choose this line, if the radius is always perpendicular, r, and this is your This is the DL. Radius is always perpendicular to this tangent. So at every point on the circle, both B and DL are tangential. So this is okay. B and DL are tangential to the circle. So at every point on the circle, both B and DL are tangential to the circle. So the angle between them is 0. As B and DL are tangential, means B is parallel to DL. You can see from the diagram the blue arrow and the red arrow DL. So now will come use. So from this line integral B dot DL, trying to solve. So this will equal to simply to B dot, we can remove BDL because BDL cos theta, cos 0 is 1, so simply we can write BDL cos 0. B cos 0 is 1, so it's simply equal to BDL. So now we can take out B also. B is constant magnetic field produced due to this current. So it depends upon only on the length of the loop. So let's go to the next page. So now further, if we go from BDL, no, sorry, I made a mistake. We got the integral DL is equal to B value we already know. At any point at distance r is simply mu 0 I upon 2 pi r. And integral of DL is simply L, or its value is 2 pi r. So you know. So our solution for integral B dot DL is equal to mu 0 into. So this is a simple proof of Ampere's circuitry law, which says, what it says, if I'll repeat, which says that the line integral of magnetic field B around any closed circuit or any closed path is equal to mu 0 times the total current passing through that closed circuit. So if we look at one by one, this is our problem. So how, from where we started, we said that let's say current I is flowing in the straight Y, and through which, and according to Biot-Savart curve, a magnetic field produced, and which is perpendicular to the plane of perpendicular to the conductor. And as let's we as we know, the radius is perpendicular, so we have considered a very small current element dl on that circle, and as we know that at every tangential on that circle, at every point tangential with the direction of magnetic field B. So at that point, and as you already know, radius is always perpendicular to tangent, so at every point r is perpendicular to B and DL as well. So B and DL are parallel, so that means B integral BDL. The angle between them is 0. Theta is 0. So I can write it theta is 0. So keeping in mind B dot, so B integral BDL cos 0 BDL, or B as B constant. So integral DL. Now to go to the next slide, we know we have already defined that Biot-Savart law. According to Biot-Savart, the current, if a current I is flowing through a conductor, then the magnetic field at a distance r from the conductor is simply given by mu 0 I upon 2 pi r. So D value always substitute, and integral of dl is simply 2 pi r, length of the conductor, which is the circumference of the circular path is 2 pi r. So B dot dl is equal to mu 0 I. Now we have learned Ampere circular law. So using that Ampere circular law, we again, this time we are using Ampere circular law to find out magnetic field inside a straight solenoid, which, okay. So let's go to the next slide, and I'll write so this time we are searching magnetic field inside a straight solenoid. Okay, I'm just shifting. Let's make it, okay, the magnetic field inside a straight solenoid. Using, so this time we are finding the magnetic field inside a straight solenoid using what? Biot-Savart law. Just like we derive Coulomb's law using Gauss law in electrostatics. So this time we are magnetostatic. In magnetostatic, we are deriving magnetic field intensity. We are finding intensity of magnetic field inside a straight solenoid using Ampere circular law. So for that, we first draw solenoid. So let's draw it. So this is a kind of solenoid. Just to make sure, more exactly, we simply draw. Okay. Now it looks like a solenoid. And as you remember, what is solenoid? What was solenoid? Yesterday we have studied. What was solenoid? A solenoid is a tightly wound helical loop from an insulated wire such that its length is very large as compared to its diameter. So many rounds of insulated copper wire is wound over in this insulated, okay, in this tube, over the tube, you can say. Now what was our magnetic field inside a straight solenoid? So many wounds. So let us define something. So let us define. Consider a very long solenoid having n turns per unit length. So remember what we are saying? We are saying n turns per unit length. Okay, in this solenoid. Let I be the current flowing through the solenoid, and I is the current. Correct. Flowing through a solenoid. And if you remember, the magnetic field lines inside a solenoid are parallel to its axis. So if we draw parallel to its axis, so this is an axis. So magnetic field has these lines. Okay, there may be more lines. Remember, okay. And let's put to add it north to south. Okay, this one is north and this one is south. So here the magnetic field direction and these arrows represent the direction of magnetic field. Now let us draw one more thing which I forget. So here in this case, what we are doing, just like a Gaussian surface earlier. So here also we are trying to draw a Gaussian surface. So let's draw with some other Gaussian surface. So I am trying to draw a Gaussian loop. Okay, imaginary loop. Let's name it A B C. That loop name is ABC. Just like we have done just now, we have done a circular loop around that straight conductor. We draw this plane conductor. Okay, in ABCD loop. So if you look at magnetic field direction, I'm just drawing, and then just putting it. Now, so this loop, this is like a Gaussian surface, so it's an ampere, you can say ampere circular surface. Let that ampere loop, we call it this ampere loop. So let the length of this ampere loop be h. Length, okay. This distance is h. Okay, now using ampere circular law, we simply go to the next one. After this, from ampere circular law, we have to find out. Let me just know. We have to first find out integral b of dl. Left from left hand side, we are starting. And that b dot dl is over the entire loop, okay. We have to find b dot dl, integral b dot dl along the loop ABCD. Okay, so what we have to do? So this b dot dl can be break down into line integral. So A to B first by part. Earlier, because sorry, my mistake. Let's B to C here plus C to D GL plus D to A BD. Okay, now each part. So here first we have to find out the value of B dot dl, the first term. This one. So let's go and add one more slide. So integral A to B dot D. So to get the value of this integral B dot del, in this case we have to first go to this diagram. As now you can see in the diagram, very much clear, that B direction is towards from left to right. Okay, the magnetic field direction B. And DL is, in this case, it's AB because we are going from A to B. So A to B is also the same direction as B. So in this case, the angle between B and DL, okay, so this A to B is 0. So we can simply write B DL cos 0. Cos 0 then, cos 0. So cos 0 is 1. So this will simply equal to A to B DL. And we can take out simply B outside from this. And while solving it, how much you got? DL, integral of DL is L. So B. So after putting, we simply got A minus B. Okay, I simply do one more thing. One more L A to B. Substitute such lower value. So this will become B A then second value minus second value A minus B. I will remove slide. Similarly, we have to find the integral B to C B GL. Now to find out the value, we again go back to this picture. Now you can see, now this time we are going from, in loop we are going from B to C, and the magnetic field again magnetic field B is along the axis of this solenoid, and BC is perpendicular to. So now the angle between B and BC, magnetic field B and the loop and the line BC is 90 degrees. You can clearly see it from the diagram. So B to C BDL cos 90, and if you remember, cos 90 is 0, so this will simply be 0. I'll simply write cos 90 is equal to 0. The reason is cos 90 is 0. Again, then C to D. Next time, how much the angle between C to D? Simply say, looking the diagram, look at the diagram again, C and D. Here C to D is opposite to the direction of B. So this time angle is how much? When the things are opposite, it's 180 degrees. Cos 180 degree is minus of what? Cos 180. But it's 180. Okay, the cos 180 is minus 1. But one more thing is here. that as we are outside the B, if you look at the diagram clearly, the magnetic field lines are inside, are passing through the solid, and not there is no magnetic field outside. So magnetic field value B is 0 outside. So that is why. So as B, remember here I am writing with the pen as B is 0. So again this term is 0. On adding one more slide, last in the list, B to A, B, DL. Again we have to look at B, DL. We are removing the fraction G to A. So B, DL cos, how much? So let's look at the diagram. This time can see it is again B to A, again 90 degrees, so cos 90 is 0. So cos here cos 90, and as you know cos 90 is 0, it means it is 0, so simply this is 0. So out of the four terms, the total integral B dot dl is simply B A minus B plus 0 plus 0 plus 0. So it is alone B A minus B. So I am making a small correction. I did it. What I did was wrong because we are moving from A to B. The first higher value should be here. So first B value should be here. B minus. So I'm just using a rubber. So it should be B minus A. So keep in mind I'll make the changes over here. So this is also I use rubber. So it is B minus A, and B minus A is simply the length, and we know the length, we already said the loop length is H. So this is simply equal to B into H. Now further going with that, so the line integral B dot, but from Ampere circular law, from Ampere circular law, Ampere circular law. Now integral B dot dl is equal to mu 0 into total current. I say net current. Simply what I wrote. In word I am writing net current. Why I am writing you will understand. Current. left hand side we already got value, it is simply BH, and mu 0 net current. It is simply net current is NH into I. How this is NH into I? N is number of turns per unit length. So total number of turns in simply is NH. So total current is simply NH into I. Okay, I'm just putting NH is total number of turns into I, total current, net current. So now from both sides we can cancel out H. So B is comes around mu 0 and I. This is the required equation which we have already got it. So by using the Ampere's second law, we have derived, or we have found the value of magnetic field inside a straight solenoid inside. Now same principle we will use to find out magnetic field. Okay, the next topic, and this for that I need use. Now here we have to find magnetic field. Magnetic field of toroidal. Okay, what is toroidal? The first question coming from the toroidal. When we bend a solenoid into form of closed loop, when we bend a solenoid into the form of closed ring, it's called toroidal. If you remember what is our solenoid? This is our solenoid. We bend into form of loop. So this will look like this. We will study later on next class. Okay, I'm leaving for now.